All right, we are coming to you live from Intel Innovation in San Jose, and we are super excited to welcome you to our second of 3 Chalk Talks. And just a reminder on the goal today, it's really to bring you along our journey as we build and deliver silicon software and platforms. Today's focus is going to be all about security, and we're going to be covering the how and the why behind Intel's security features in our upcoming, highly expected 4th generation Xeon processors. We have got a great program for you today and 2 amazing speakers. So we want to make sure that this is conversational and interactive. So just some ground rules before we get started here. For those of you who are online joining us, please put your question in the chat, remain on mute, and then when we get to the Q&A portion, I will make sure I answer your question directly. And when you have questions in the audience here, just raise your hand. Megan is going to have the microphone, and she'll be walking around to make sure that you guys get your questions answered, because we definitely want to make sure you're able to ask your questions while Anil and Amy are here. So without any further delay, I am going to hand it over to our fabulous Anil, who's going to give you some context on who he is, what his role is, and why security matters to Intel.
Thank you very much, Casey. Good afternoon. My name is Anil Rao. I'm responsible for security and systems architecture in the office of the CTO at Intel. Now, before we really start off on technologies and topics and everything, one of the things that I want to make sure everybody knows, understands, and realizes is that security is a top priority for Intel. When we say security, we kind of focus on 4 fundamental areas. Security as a mindset, because issues and vulnerabilities can happen anywhere, and it is a mindset. It's important for every engineer in the company and every engineer in a partner organization to understand that they need to think from a mindset perspective. Second is technology. Today we're going to talk a lot about security technology. Third is assurance. Things happen, things break, and how do we react and make sure that we address any type of open issues and things like that. That's the third one. Last is protecting ourselves, because we are a large company and an organization. Create these best practices that we can then share with the broader industry. And we use the term cybersecurity for that particular group. Now, products built with security inside of Intel go through a tremendous amount of rigor. Security starts off at Intel by design and development practices. It goes right to the core of what we do. Security is also something where we support throughout the product's lifecycle, whether the product lifecycle is short, maybe 3 years, or whether the product lifecycle is long. We do have security processes methodology in order to support our customers and our products out in the field. Now, going into security in the data center area, we focus security in 4 specific areas. And these areas are confidential computing, crypto acceleration, software behavior, and last but not least, platform integrity. Now, the Intel 4th generation Xeon platforms, Sapphire Rapids, improve each of these categories, and we'll look into some of those things. Now, today, from a security perspective, we're going to focus on 2 fundamental areas. The first is we want to give you an update on confidential computing and share some new information about large baseline SGX enclaves with the 4th generation Xeon. We'll also talk about other products like Grameen and Amber. And second is we'll review Intel CET, a safe software behavior. This is a feature that is also introduced on the 4th generation Xeon Scalable platform. Now, let's quickly recap what confidential compute is and what is SGX. We've long protected data at rest and data in transit as an industry. Now, these days what is happening is that there is a tremendous amount of insider attacks and even memory scraping, privilege escalation attacks that's happening inside the industry. So vulnerability exists not only in terms of data in transit or data at rest, but also when data is in use, which is inside of the memory. Now, confidential computing as a technology is invented to address this last mile problem with data encryption and data protection. There is a tremendous amount of momentum that we see in the confidential computing. There is the Confidential Compute Consortium. There are major CPU vendors who are working on confidential computing technologies. And most major cloud ISVs are working in order to bring or have already brought certain elements of confidential compute technology into their infrastructure. Now, how does confidential compute work and what is confidential computing, right? I want you to step back and take a look at it from two fundamental ways. The first is that you want to isolate all the work that is happening using an isolation technology. I'll talk a little bit about that. The second is that you want to attest to what is being isolated to make sure that the attestation technology confirms that the underlying hardware, underlying infrastructure is safe and secure. Now, isolation sequesters code and the data associated with the code, and it runs inside something called a trusted execution environment. TEE is the short form for trusted execution environment. And in this scenario, only authorized software is allowed to access the data inside of the TEE. Any data which is outside, or any operational software which is outside of a trusted execution environment, even if it gets access due to some issues or bugs or anything of that particular nature, the data is opaque. It's completely encrypted and you don't have visibility to it. Now, Grameen is one of our open source isolation library operating environments, which allows for unmodified applications. Just take your application which is existing today, and using Grameen, you can run it inside of an SGX enclave. Isolation alone doesn't guarantee that everything in the environment is protected and it is secure inside of a TEE. And this is where you need another process which is called attestation. Now, what does attestation do? Attestation does a couple of things. The first one is that it ensures that you're running a genuine Intel SGX CPU. Second is that it ensures that the microcode, the firmware, and everything which is running inside of the TEE is up to date, and any of the IPU patches that may need to be applied is fully applied. Third is that the software that is loaded inside of the TEE is trustable and it's exactly what is expected to be inside of that TEE. Now, obviously, attestation is a mechanism where you go outside of the TEE in order to run and operate the infrastructure. And how do you and how does Intel make it easy? Greg Lavender was talking about Project Amber. We also had Liz from Lidos kind of like talking about Project Amber. Project Amber is Intel's independent trust authority service. It enables and provides organizations with remote verifications and trustworthiness of compute assets inside of a cloud or on the edge or on-prem environments. This Amber operates separately from the infrastructure or the operator. So this kind of reinforces what is the fundamental premise of confidential computing, which is to take the operator outside the trust boundary. So with the TEE and with Amber attesting to the contents of a TEE, you know that the operator is fully outside the trust boundary, and this comprehensive solution helps provides objectivity, independence to enhance and provide assurance on confidential computing to end users. Now, we've been talking of SGX and confidential computing as technologies, and Amy is going to talk about some of the additional technologies that we're working on. It's not just about protecting the infrastructure, right? A lot of times when we talk about security, we think of protection. Protection is an important element. But the beauty of some of the things associated with confidential computing is that it opens up new use cases. It opens up new opportunities. Now, our customers find additional value beyond just the basic security capabilities. Some of the motivations that compel our customers and end parties to use confidential computing are things that I'll talk about. The first is that it strengthens control of their applications and data. So as we spoke about, it keeps these things private even when you go and operate it in a public cloud or in an edge type of like a cloud. Think of it as having your own private cloud inside of a public cloud scenario. That's what confidential computing provides. The second is that it enables sovereign data movement, which is a key factor. Data is generally the asset of the data owners. Sometimes it's also the asset of states and nations. How do you make sure that the data that you generate is completely under the control of your organization or your state boundary? And confidential computing enables that particular capability. Second is that many customers who work with regulated, private, or business confidential data have to meet certain compliance kind of like rules, whether it's GDPR or HIPAA or PIPL, which is in China. This requires higher standard of care when handling customer data. And I'm going to talk a little bit about some of the use cases where you'll see that confidential compute has indeed enabled better type of like computational operations when you're operating under these stringent conditions. It lowers the risk of breach, and it also enhances some of the compliances, enabling multi-party computation where you can pool data, you can even pool analytics from different organizations without any single organization giving exposure to their data to other organizations. Third, customers strictly interested in security properties. These days there is many sophisticated attacks that happen on machines. And when you start looking at it saying that, look, I need to deploy it in public cloud, I need to deploy it in edge cloud, or I need to deploy it in clouds where I don't have access to physical infrastructure, how do you take care of this? Confidential computing enables a better protection of data there as well. Think of it as providing an armor where your data is opaque. So even if certain malware attacks or infiltrations happen, the data is protected, which is the fundamental IP that you as a corporation own is fully protected. And this is an area where there are a lot of active sectors, whether it's that industries handling private data, regulations, healthcare, financial services, government, all of them, whether it is high privacy, regulatory, or security concerns are critical elements. Customers really want to use this type of technology in those areas. Last but not least, some of these new emerging use cases include things like privacy-preserving ad tech, consumer interests in analyzing ad targeting companies without exposing personal data, confidential blockchains, and one of the biggest and the largest area is confidential AI, where multi-parties, whether it's in the finance segment, healthcare segment, or even in regulated industries, what they can do is they can enable multi-party compute where the algorithm handles confidential information and regulated data inside of these TEEs while enabling end customers and end data providers to be compliant with the government regulations and for the data to be private there as well. Now I'm going to hand it over to Amy for her to walk through some of the details on these trust boundaries so that you can understand how these different technologies work and why confidential computing, whether it's SGX or TDX, are the right kind of solutions for our end customers. Amy?
Thanks. So as Anil was saying, the trust boundary is what differentiates the trusted execution environments from the regular virtualized cloud service providers. So what you're seeing on the slide today is an example of the trust boundary that exists today in a cloud service provider's multi-tenant sort of environment. There's many parts, many software and people who could have access to the data in there. And so for example, you have your protected data on the right, and then you have your application that has to work on the protected data. But the guest OS that is hosting the application could also get to the data. The virtual machine monitor that's typically provided by the cloud service provider could conceptually get to the data. And then you have your certain admin privileges that exist either in the guest OS or in the cloud service provider's purview, and all of that could get to the potential data. So when we talk about trust boundary, we want to minimize the amount of things like attack vectors, right? And by minimizing the trust boundary, we are able to minimize the number of attack vectors that could go after that confidential data. So this next slide shows basically the difference between a VM isolation technology, which is like Intel Trust Domain Extensions. AMD also has one called AMD SEV SMP. And then the bottom one is Intel SGX. So with a VM isolation technology, a customer who's going to the cloud could take their own OS as well as their application stack, put it into a trust domain VM, put it out on the public cloud, and they are protected from the cloud service provider's software stack, right? So we minimize that trust boundary from regular multi-tenant virtualized to trusted execution like a TDX, where the cloud service provider software stack is out of scope for getting to that protected data. Now, if you want to go even further, that's where Intel Software Guard extensions come in. And a Software Guard extension, you can get the minimal trust boundary. You can get it down to the application. And depending on your application could be small or large. As Anil talked about, there's Grameen that'll take your whole app and wrap it in a live OS, and that all of that software would be part of it. Or if you're you have particular data sensitivity and you want to minimize it, you could write a function. Tens of lines of code could be in an enclave that is on working on highly sensitive data. And so as you see, between trust domain extensions and software guard extensions gets the OS, the operating system, as well as the virtual machine monitor and all of the things trust domain TDX gets out, but it makes it even smaller. And with a smaller trust boundary, it's more defensible and less attack surface. So you have more control. And I'll hand it back over to Neil for customer examples.
So one of the things that I think about when it comes to SGX and TDX, like Amy was talking about, right? It's like I always think about this as your hotel room. When you go into a hotel room, you have a safe. So if you want to protect your wallet, you want to protect your passport and things like that, you put it in that safe. That's SGX as a technology. And Grameen allows you to say, you know what, just tell me whether you want the entire application to be put in a safe. I'm going to put the entire application and run it into a safe. And an application theoretically can even be a virtual machine. What TDX does is to say, I'm just going to protect your entire room, right? So you don't need to worry about anything. I'm going to work with the hotel operators, and I'm going to protect your entire room. That's why we feel that Intel provides you the flexibility in terms of solutions and the offerings. And the customers can choose what it is. And today, SGX as a technology is available, starting with our Ice Lake. But we're going to have other technologies come in terms of TDX in the future. Now, I want to talk about two specific use cases where it kind of talks both about the larger use case model and also in terms of the protect and enabling of different types of solutions. So let's look at two use cases. One is our customer Bosch, and the other one is UC Santoni. Now, Bosch is a global leader in technology and manufacturing, and most of us know that. What Bosch wanted to do is that they wanted to build an autonomous driving solution, and they collected a lot of images in order to train their autonomous driving solution. And most of us know that when you collect a lot of images, you generally go and have these cars out in the open, you collect the images. Those images will have PII, personally identifiable data. Like your faces may show up there. Your cars with your license plates may show up there. And maybe certain stores and store titles and names and addresses may show up there. And some of these things are sensitive information that you don't want everybody to kind of like have access to it. So what Bosch did is that they did two things. One is they did a desensitization where they used these images, removed all the PII, personally identifiable data, from these images, and all of these things were done inside of an SGX enclave. And then they took the raw footage and started to identify these things, saying that here is a human, here is a car, or here is a license plate. And then they brought the two back together, because once the marking or labeling, like what Andrew was talking about this morning, now once the labeling happened, they brought it back into an SGX enclave and then trained the entire system with both PII and non-PII data. Now, the training was done completely inside of an SGX enclave, so all the rules associated with GDPR and everything was met, but also they could leverage a multitude of corporations, companies, and other things in order to do the labeling of the data, because they didn't need to take it through an expensive labeling process. So it resolved a lot of issues, and it made TCO efficient for Bosch in order to adopt a technology of this particular nature. The second one is UC San Francisco, and this is an example of multi-party compute, where UC San Francisco actually leads a collaborative research with multiple hospitals. Now, each of the hospitals needed to bring their data. So all of us know that HIPAA and other regulations make sharing of this data a lot more challenging. In the past, if you want to share some of these pieces of data, you have to go through like data escrows or anonymization of these pieces of data, which made it tremendously cumbersome. And sometimes when these things happen, you lose a lot of time. What UCSF did is UCSF collaborated with another partner company of ours called Beekeeper AI. They created a system where information is pooled inside of an SGX enclave, And the information is then processed and all the training is done inside of an SGX enclave, whereby the constituent hospital data is still kept confidential because it's not something which is exposed to others. What this did was that this enabled faster research, superior analysis, because a lot of other hospitals came in and said, oh, if you're going to do it inside of an SGX enclave, then I can give you my data because I do know that you don't have visibility into it. I'll release the keys when I know that the enclave is secure, right? So they did all of these things in order to get that faster research without any lengthy anonymization process or HIPAA compliances that they needed to go through. So what I want to talk now is some of the interesting things that are coming in the 4th generation Xeon scalable processors. Now, in the 3rd generation, we had a base enclave size, which you can see ranging anywhere from 0 all the way to 512 gigabytes. So you could get all the way up to 512 gigabytes if you wanted for SGX as a SKU. But in working with our customers, we felt, and the customers gave us feedback, that the base enclave size or the baseline enclave size on each of these SKUs needed to be larger. So in the 4th generation Xeon, you will see that we will have larger base enclave sizes. What this does is that it opens up huge opportunities for a lot of our customers to use SGX as a technology in order for them to run either part of their application, like what Amy was talking about, or the entire application inside of an SGX enclave. This enables confidential computing, either for pieces of your code, processes, functions, entire applications, or even complete virtual machines if required. Now, this is mostly about confidential computing. I'm going to pass it on to Amy to talk about CET, which is Control Flow Execution Technology.
Thanks, Anil. All right, so we'll talk about control flow enforcement technology, which is a new capability for Xeon platforms. This was first introduced in our client systems on our 11th gen Intel Core processor, but for the Xeon line, the 4th gen Xeon Scalable will be the first time we actually support the CET. So CET, what it does is it protects against a whole set of attacks. There's certain attacks where when you do a call or a jump or a return, as you're jumping around within your code, it will protect against those class of attacks. ROP, JOP, COP is what they're known. And so how do these attacks work? These attacks work is it takes code that already exists, valid legal code, and it stitches together pieces from that valid code to do something malicious. And so this is an example of from the Gettysburg Address. I pull certain things out and create malware from code, right? So I take little snippets, and it's just the order of which I take those snippets. I control that, and then I'm able to do an attack there. And we'll go a little bit more into that. So with control flow enforcement technology, CET, we use there's a controller gadget that organizes the sequence of the flow for what you want to do. So it jumps from here to here to here to here to get the sequence that it was trying to do for the malicious code. The controller can be, when I put things onto a stack, the buffer overflows can corrupt the stack and change where I should be jumping to. So I thought I was going to jump to X, and I corrupt the stack and I jump to Y. So that's essentially how the attack is done, whether with jumps or returns. So CET uses hardware to stop these level of attacks, and I'll talk about the details of that. So the first is a shadow stack. So when I do a return instruction, the information about where to return to is written on my execution stack. And that stack is writable by software, controllable by software. What we do is we create a shadow stack, which is hardware controlled only, and so we will push the same information. So then when I go to do a return instruction, I compare the shadow stack to the execution stack, and if they're different, that throws an error. So we stop the attacks where people change the return instruction by creating a shadow stack and doing a compare before we do those. So that takes care of the return. Next, we have a new software capability called to track branches. And so we've enabled compilers, And we have a new software flag called enbranch. So with the CET-aware compiler, the enbranch is placed at legitimate starts of the code. So instead of being able to jump wherever I want in legitimate code, what the enbranch does is it says, I only allow you to branch to this area. And if you branch somewhere else, that will be an error. So the compiler puts the enbranches in. So jump and call commands are only allowed to land where the people writing the software wanted it to go. And we have the hardware enforcement to say, hey, if you're jumping to somewhere where the software person said you cannot jump to, we will throw an error. So that gets rid of our jump and call attacks where you jump and call to snippets of code. So anywhere within the application, we limit that with the enbranch instruction and the CET hardware that we do. So CET will render these return, jump, and call-oriented programming attacks obsolete. And it'll be standard. It's available across all of our SKUs in 4th Gen Xeon Scalable.
Thank you so much to both of you for taking the time to come here and talk about this very, very important topic. Thank you so much to everyone who's here in our live audience. Thank you to everybody online for joining us today. We had a great time with you, and we hope you had a great time as well. We're really looking forward to bringing everybody back to our 3rd Chalk Talk, which is going to happen later this year. So be on the lookout for more updates there. But otherwise, it was really great having you all. Thank you so much.
Thank you very much.
Thank you.
Appreciate it.